Die Sprachübertragung beginnt jetzt. Alle Teilnehmer befinden sich im Zuhörermodus.
Good morning, ladies and gentlemen. I warmly welcome you to today's Wired Technology webinar. My name is Melanie Börder. I am working in Wired's marketing department and I will guide you through the program. First, I would like to inform you about some technical matters. Please note that it's important to mute your microphone in case you are logged in through your phone. But don't forget to turn on your speaker so that you can hear us. If there will come up questions during the presentation, please don't hesitate to transfer them to us via our chat. Just type your questions in this field right under the green field and press send. We will then either give you an answer back via the chat or talk about it in the discussion after the webinar. If you get logged out during the webinar for any reason, please repeat the login process the way you did it before again. To figure out what our audience works with, 2 questions will appear now, and it would be nice if you could answer them. This way we are able to focus our content of webinars on our customers' needs by finding out the topics of interest. Okay. You can now see the answers of these questions. Are you using SEC GPC regularly? It's 73% using and 27% of you not using SEC GPC regularly. There's also another question. So do you frequently have samples which are difficult to separate? And you here see also the result. 85 of you are using samples which are difficult to separate, and 15% don't have much problems with the separation. Thank you very much. We will now continue. As you know, the webinar is titled Asymmetric Feed Flow Fractionation AF4, a powerful alternative to SEC. On the basis of application examples, we will point out how AF4 can optimize your separation projects, and how that exactly works will be described by Dr. Roger Scheras. He is Senior Application Scientist at Wired Technology, and I will now hand over the microphone to him.
Yeah, thank you, Melanie, for the kind introduction. So I will try to explain you today how FFF is working and how it can help you to overcome problems with other separation methods, or to give a method which allow you to separate your samples like particles and very huge polymers which normally do not run over a normal SEC column. So first of all, I want to explain what field-through fractionation is. It is a kind of liquid chromatography. You can use it as an alternative method to SEC, as explained, and it separates molecules and particles. The separation relates on their size, so that means the hydrodynamic radius or diffusion coefficient. The separation does not take place in a stationary phase, so it's a stationary phase-free separation method. Look more into detail. You see here we have the channel, and in red we have the channel flow. You see that's the channel flow in, and here is the channel flow out. Then the yellow flow is the cross flow, so that is the flow which goes through the membrane. The parts of the channel are here in the picture below. So this is the lower plate where the frit is in, and the O-ring to tight the channel. On the frit we have a membrane with different cutoff. We have membranes of 5, 10, and 30 kilodalton, and also lower cutoffs of 2 kilodalton or even lower up is possible. Then we have the spacer. The spacer is a foil which forms the separation channel. And on this foil we put the upper lid, and in the upper lid we have here a macrolone inlay so that it is possible to look through. And with that you can see air bubbles, for example, or you can even see the separation of colored samples. When you make a separation with FFF, you see a very huge difference between SEC and FFF. And the main difference is that in SEC, first the dimer elutes and then the monomer. So the purple line here is a separation with a TSK 3000 column, which is a very well-known column in the protein world. And the green measurement here is the monomer and the dimer of BSA if you use standard Superdex 200 10 by 300 column. Also a very well-known column for proteins. If you compare that with FFF, we have here the 490 micrometer spacer. So that means this foil here, which forms the channel, is 490 micrometer in thickness. You see that we separate the monomer here, but the dimer elutes later than the monomer. That's the opposite than in SEC, where the dimer, so the bigger particles, elute first. And the reason for that is a separation mechanism, which I will explain you in the next slides. And when we increase even the separation, you could even separate fragments from the BSA, which is not possible with classical SEC columns, but in our days with the newer UHBSC SEC columns, you can also separate this fragment from the main peak. The nice thing that we do not have a stationary phase means that we have less absorption problems compared to classical SEC, and we also have less shear stress of the sample. And that is the reason why the FFF technique is the technique of choice in case that you want to separate particles or liposomes or viruses or just relatively fragile material which does not like the shear force of the column or which just absorbs on the column. And this you will also see later with my examples. So let us go more into details of the separation. The separation, as I mentioned before, takes place here in this red zone. And the yellow flow here, that is the cross flow. What does that mean? When we pump in the flow here through the main channel in bore, we use one pump. And this one HBSC pumps produce a flow of 4 milliliter per minute. Then we have here on this side, and the channel out, the detectors. And of course, the detectors produce a lot of back pressure. Usually, that's 5 to 10 bars. And below the membrane, there the crossflow comes out. And the crossflow does not have a back pressure. So that means if we pump liquid in, it would prefer to go out here. But what we do now is we measure and control this flow by a Cori flow controller. This Cori flow controller measures the amount of flow with the Coriolis force. That's a very accurate measurement, which is absolute, and not a function, for example, of the density of the solvent. And it also contains a valve. So with the measurement and the regulation, it can regulate the amount of flow more precise than an HPLC pump, down to 0.02 milliliter per minute. So to a very, very low crossflow, which is very often useful if you want to separate very huge particles. Now we put in the sample. The sample sees the crossflow, and the crossflow presses the sample down towards the membrane. Normally, the membrane is slightly negatively charged, and if we have negatively charged sample, then it's very easy, because then you have repulsion between the sample and the membrane. If the sample is slightly positive, usually the separation is also possible. When you press, or when the crossflow force the sample down, the sample tries to work against that by its diffusion. The smaller the particles are, the more they diffuse, so they have a higher diffusion coefficient. And that leads us to the fact that the smaller particles are, in average, a bit higher in the channel than the bigger particles. When we look now to the transport flow, which flows through the channel, then this transport flow is a laminar flow, and that means that near the membrane, the flow velocity is roughly 0, and the higher we are above the membrane, the higher the low velocity is. And the strongest difference is in roughly 10 micrometer of the channel. So the total channel height is 490 micrometer, and just in this 10 micrometer below, above the membrane, there is a separation takes place, because in these other regions, the difference of the flow velocity is not high enough to achieve a good separation. So this flow velocity transport the particles to the channel outlet. And the crossflow force the particles down so that this equilibrium between the bigger and smaller particles stays constant. And during the separation, the smaller particles elute first, because they are in a field where they are more in contact with the higher flow velocities. And that's the reason why the smaller particles elute now first. If we take a look at the chromatogram, it looks like this. So we have at 5 minutes the void peak. You see here just a very tiny peak because of switching of the valve, and maybe some very big aggregates which elute, but that's here nothing. Then you have the first monomer peak at roughly 9.5 minutes, and then you see the dimer peak of the BSA at 11 minutes. So BSA is our favorite sample because it's not so expensive, and you get it in a very good quality with always the same amount of dimer in it. So it is a very good sample to test if the separation you achieve with the system is okay or not. And that's why it is our favorite sample. And we have again here a pump flow of 4 milliliter per minute. This comes into the channel, and then the FFF splits the flow so that the cross flow is regulated to 3 milliliter per minute, and that means 1 milliliter per minute is left, and this 1 milliliter per minute goes through the channel outlet to the detectors. Here in this example, we injected 20 microgram of the BSA. So that's a quite reasonable amount of sample, which is comparable to an SEC column. And as detector, we use here only the UV detector. And you see also that at the end of the separation, you see the aggregates. That's also different to SEC, because in classical SEC, these particles, they elute in the exclusion volume of the column. And when they elute there, and maybe they anchor a bit on the column bed and so on, then they are also visible with later elution times. And then they can co-elute with your normal sample and disturb your molecular mass distribution. And it also disturbs, of course, the light scattering measurement. And very often with an FFF separation, you can overcome this problem. When we go more into detail on the experimental setup, so you can use different HPLC lines. So here are two examples with an Agilent and with a thermo HPLC line. From the HPLC line, you have the eclipse, which regulates the flow, and then the separation takes place in the FFF channel. From the FFF channel, it goes to the channel outlet, and from the channel outlet to the UV detector as first detector in row. And there it could be a VWD, an MWD, a DAD, so you could even, of course, collect a whole spectrum. And with this, you can measure the concentration. And it also gives you when you have the extinction coefficient, a precise information about how much sample elutes at which time. But up till now, you did not measure the size. And for measuring the size, we normally add a miles detector. There is a way of predicting the size from FFF theory, but for an absolute measurement, you need the miles. The miles detector measures then the amount of scattered light at different angles, and we can measure from the angular dependency the radius, and from the intercept of the y-axis of the Zim plot, we can measure the molecular weight of the sample. For this measurement, we use a concentration detector, and this could be the UV, which we had in front of the light scattering, or we can measure the concentration with the DRI. With the DRI, we have the advantage that a protein has usually a constant d/c of 0.185, so it's not necessary to know the extinction coefficient, and quite often it's impossible to measure that. You would even see material which have no aromatic amino acids in it. And another advantage of using DRI is that the DRI detector uses the same constant as the light scattering detector. And that makes the formalism much easier and reduce the error. After the DRI detector, we have the possibility to let it flow to the waste, or even to collect a fraction collector. This could be, for example, used if you want to do more studies with the material, like electron microscopy or ICP-MS or something else. Yeah, here again, you see the HPLC setup with the wired instruments in a rendering. So the FFF setup is a one-pump solution. All the other flows are generated just by this, by the splitting of the pump with some valves. And we integrated the software control in the Agilent ChemStation software or in the Chromeleon software from Thermo. And with these two HPLC lines, we use the the most used HPLC lines on the market. And if you want to integrate other HPLC lines, you can do that as well via the Chameleon software. Of course, the FFF is specially designed to integrate it with the wired Miles detectors. It has the same size of a chassis, for example, and of course all the connections are that you can easily plug it in the other detectors for auto starts and so on. Another advantage of using this setup is that it is very easy to use the same HPLC as well for FFF and for SEC. And this could be even be done automatic by a valve inside the Eclipse. So then you need to use a FFF system with a switch option. And that automatically switch between SEC and the separation channel. It is also possible to use the HPLC manually in SEC mode. That means that you have to change free flow connection and bypass the Eclipse. And then you can use the whole setup with the UV, the Miles detector, and the RI detector from Wired just for normal standard SEC measurements. That's very often done by customers because you get more information if you use different separation principles. And yeah, with this I come also already to the examples. So first example I want to present you is the amyloid beta 40. So this peptide has a strong tendency to aggregate. And if you measure it on a SuperDex 75 column, you get a very, very strange result. So you see here, you have here some peaks. So around 20 milliliter, we expect at this column the solvent peak. It should usually be at 18 point something. And you see that makes sense that the main peak eludes quite close to this solvent peak, but the molar mass we measure for it makes no sense at all because it's very noisy. It's around 100,000, and then here the molar mass goes up very rapidly, and also here between 14 milliliter and 8 milliliter we have a constant molar mass. So that means in this region we do not have any separation. And when we now look at the second detector, the light scattering detector, then we see, well, we have here the main peak in light scattering. That means a lot of aggregates elude here, or very high molar mass aggregates. And they are so high in molar mass that with this very tiny UV spectrum, we cannot measure molar mass here at all. So it just looks very strange. And then we decided to use or to measure this peptide, which has a molar mass of roughly 4,600, with yeah, the FFF channel. And when you do so, you see suddenly, indeed, a monomer. We have a very nice monomer peak here. We have a very flat monodispersed molar mass. And so that's a really reasonable separation of the amyloid beta. And you see here the UV trace. And in the UV, you see here at 20 minutes also a peak. And this peak is just because of the aggregates. So we have here the monomer, and these are the aggregates. And because of the FFF theory, they elude later than the main peak. And so in roughly 30 minutes, we can establish a very nice separation of the amyloid beta. The FFF can do much more. So one thing is that we set the autosample to 40 degrees. And then we measured every 2 hours a run. And when you do so, you see that the area below the peak is decreasing. That means with time, so 10 o'clock, 12 o'clock, 2 o'clock, and 4 o'clock, the area decreased. So we get less and less monomer. And if you plot this here, you can calculate from this a very nice kinetic. And you see the fit is quite reasonable. Yeah, and the existing, or with this aggregation built very big particles, you cannot separate anymore because they are bigger than 1 micrometer, and maybe they precipitate in the vial, so we couldn't see them. But you see very nicely the decrease of the area of the main peak. Another example I want to show you are virus-like particles. Virus-like particles, normally you have a protein which forms these particles, and then you produce that, put that in solution, and then it forms this virus-like particle automatically. And these are usually very huge particles of 20 to 100 nanometer, depending on the kind of particle you want to produce. And normally, if you use an SEC column with virus-like particles, they elute all in the exclusion volume. So no chance to separate them. But in FFF, that's possible. So you see here, that's a virus-like particle, which has 2 species. But these 2 species are not monomer dimer. That would be too easy. But these 2 species, they have 16 and 18.5 nanometer. So the difference, or at least the ratio between this, is very small. And it's very good that we get a separation here. And it's nearly baseline separation. And what are these 2 species here? It is the first species has 180 subunits, which correspond to a molar mass of 3.4 megadalton. And the other species with 18.5 nanometer has 240 subunits, which with a molar mass of 4.8 megadalton. We have a very nice signal to noise because the sample is very big, so we have a very good light scattering signal and a reasonable UV signal. And with an injection of 1 microliter with a solution concentration of 2.3 milligram per milliliter in a PBS, we achieve this very nice separation with very good signal to noise. And the last example I want to show you are liposomes. So liposomes are also very fragile because they just normally they are round particles formed by a layer of fatty acids. And what you see here is this was a nanodisk. And this nanodisk is formed if you have this liposome and then add a special protein to it. And this nanodisk is usually quite stable. So it should be possible to separate it with an SEC column. And the customer used the SuperDex 200 increase, which is normally very gentle to most of the proteins, and even difficult proteins, normally it's no problem to separate it with a SuperDex column. When we do that with a flow rate of 0.7, that was the flow rate the customer usually use, you see 3 peaks. So there's one shoulder here, which with a different molar mass behavior on the column. Then we have the main peak here, and we have another shoulder here, and some very big aggregates here on this side. That looks quite normal, and the customer was happy with that. Then we tried another flow rate, because we had the feeling that because of the light scattering information, something is wrong. I will show that in the next slide. But when we use the flow rate of 0.1 milliliter per minute, you saw or you see a totally different chromatogram. So you see that this shoulder is a bit stronger here on this side, and you see a 4th peak here with a huge molar mass. So it means that there is somehow interaction with the column bed. Another, normally very nice information is that we have less aggregates here at the beginning. But instead of the aggregates now, we have this very huge peak at 10 milliliter. And it's very difficult to interpret, to explain that. But it seems that this high flow rate of 0.7 together with the column bed destroy the high molar mass samples. And another problem is just the separation, which you can very nicely see in light scattering. So in light scattering, when you take a look here at 18 minutes, for example, at this time frame and this slice of the light scattering plot, you see you have, because that's 1 divided by Rayleigh ratio, you see that the lower angles, 2, 3, 4, they have a huge light scattering signal. And you see the fit is very bad. And you cannot fit it because it's not just one single particle that's elute, but it do the different species. So it elutes very big aggregates and the small particles, what normally should elute there due to the normal SEC mechanism. And this co-elution is the reason why you cannot fit it with light scattering. So the results you get for the molar mass and also for the radius are quite wrong. When we use the lower flow rate, then it's very interesting that this behavior is much, much less. So you see here already the arrow bars, and that is a sign that we have much, much less scattering to the front, so that means much less co-elution than with the 0.7 milliliter per minute. And then we used a similar sample in FFF. And for this sample, you see that we have a very nice separation of the molar mass between roughly 80,000 up to a little bit less than 1 million. And that is much less than in SEC. And here with this other SEC run, you see again that the behavior of the sample on the SEC column is very strange. So you see here the blue line that it comes from a high molar mass, goes down and goes to high molar mass again. So that is maybe due, or most of the time due to co-elution here from the bigger particles and so on. But in FFF, we do not see that. And even in the light scattering trace of FFF, there is no sign of co-elution of bigger particles. And also at the end of the chromatogram, no signal, no bigger particles were observed. So FFF is here really a solution to keep this fragile molecule together and to be able to measure a reasonable size and molar mass. So with that, I want to summarize my talk. So I hope I could show you that FFF is a liquid chromatography method where we have no stationary phase and the separation takes place or happens due to the hydrodynamic radius of the sample and the diffusion coefficient. That we have a lower separation limit depending upon the cutoff of the membrane. So the lower limit is usually 5 kilodalton, but we also have 2 and even below 1 kilodalton membranes available. And the upper limit is roughly 1 micrometer for molecules and particles. The flow rate and sample requirements are comparable to SEC. Usually we use a little bit less sample because of the missing stationary phase, better signal to noise. And due to the demands for the separation, we can use different channel geometries, different channel heights. The duration of a separation is roughly between 15 and 120 minutes. And the amount of sample can differ from 1 microgram for an analytical run to up to 2 milligrams for a semi-preparative run. And where should you use FFF? So it's optimal if you have very huge particles, bigger than a few hundred, or if bigger than 50 or 100 nanometer, because normally this you cannot measure or separate by a SEC column. And Then, of course, if the particles are getting even bigger, FFF is a good option. And it's also the method of choice if you have a very sticky sample or very fragile samples, like the liposomes I showed you before, but also particles. Yeah, with this, I want to thank you for your attention and give the micro back to Melanie. Thank you.
Thank you, Roger, and thank you, ladies and gentlemen, for your attention so far. Now we will answer some of your questions. So we have, what would be the smallest and the biggest particle that can be analyzed?
Yes, I mentioned before, it's the question of the cutoff. The cutoff of the membrane, of the standard membrane, for example, is 5 kilodalton. But 5 kilodalton does not mean that a protein can really be 5 kilodalton, because this membrane cutoffs, they are measured with polymers, and these are linear molecules. So they are much bigger compared to their molar mass than a protein. So usually, to be sure, we always say that you should be 2 to 3 times bigger in the, or higher in the protein molar mass than in the cutoff of the membrane. And we have 2 kilodalton membranes available, and we have also some lower than 1 kilodalton membranes. But it's always difficult. The smaller the sample is, the more cross-flow you need for the separation. And the smaller the cutoff of the membrane is, the more difficult it is to get the high flow rate through the membrane. And so usually you need then, you take then channels of higher spacers. But you can solve all these problems, of course.
Thank you. The next question. With MALS, do we need a refractive index data of a particle?
That depends. So if you have it, it would be optimal, because that would mean a real concentration measurement in milligram per milliliter with DRI, and it allows you also to measure the molar mass. But usually with particles you are not interested in molar mass, but you are more interested in the size and in the amount of particles. And if you just want to know the amount of particles, then our light scattering software has a particle module, and this particle module can count particles if you know the refractive index of the particle. And that is also patented, and you can find it in literature or in the internet how it works. So in principle, it looks at the scattering function and measures the size, and from the light scattering intensity, then it measures then the amount of particles in the peak.
Okay. The next question is regarded to one of our examples in the presentation, the retention time. Did the retention time shift over time for the A beta?
Yeah, that's true. That happened. Yeah. I can go to this example. You see here with time, you see a shift. And this shift is quite strong. So it's really a few minutes. Of course, there can be slightly shifts in retention time when the temperature changes. But normally in FFF, when you have a constant temperature, you always have the same retention time. If you not have the same retention time, then it can happen that the reason is that maybe the membrane change over time, maybe due to the aggregates which precipitate on the membrane, and then the charge of the membrane change. And then the particle has more repulsion or more attraction, and then is higher in this flow velocity profile in the channel. And then you have different retention times. So I'm not so the temperature here is not the case. So I'm definitely sure that it's something else. Maybe the membrane is changing due to the aggregates. But that's also the reason why we measure with light scattering, so that you can measure the molar masses there and you can be sure that this is the dimer still, and not maybe a the monomer still, and not maybe a dimer or something.
Okay, next question. What is the maximum sample volume that can be loaded in the FFF?
The maximum sample volume, that depends on the autosampler. So normally we recommend an autosampler with a 900 microliter loop, because then you're limited to 900 microliter, which is of course a lot. The point is that we have a focus step where when we put in the sample, we focus it as well, and then we concentrate it on a special region in the channel. And so it doesn't matter how much volume we inject. Just if we need to inject more volume, we just focus longer, and then we can separate the same amount of material. In case that you want to, for example, measure lake water or something where the concentration of the particles is very, very low, then you could still use a manual injection loop where you can inject 10 milliliter, for example, or even more if you want. But then just the focus inject time would then be maybe 10 minutes or 20 minutes instead of just 2 minutes when you inject 10 microliter. So you are very flexible in this with this focusing. So that's totally different than in SEC.
Thank you. Would it be possible to differentiate filled particles or liposomes from empty ones?
Yes, that's possible. We have also some application notes on our webpage for that. And you do that with the hydrodynamic radius and the radius of duration. When you have an unfilled liposome, then usually it behaves like a hollow sphere. So that means that the hydrodynamic radius measured with a DLS instrument online, so our Wyatt Quells, for example, and the radius of duration measured with the Miles detector is nearly the same. So the ratio is 1. And the more it is filled, the smaller the ratio gets, because the radius of duration sees the particles also inside and is getting smaller, and the radius of the hydrodynamic radius stays constant. And this ratio can be down to 0.78. That is the 0.78 is the ratio of a compact sphere. So that's the lowest possible value. And of course, another method would be to look if you have a chromophoric group in it and you can use the UV detector, then this will also give you an additional information.
Okay. How much work do I have to invest to establish an AF4 assay for an unknown protein?
Oh, that's not so easy to say. So if it's really totally unknown, you can be lucky that you do 2 runs and the method development is finished. You can be unlucky and it takes a few days. It always depends, you know, if it works with the normal standard membrane. If the recovery with the standard membrane is okay, because then you do not need to screen different membranes. It is a question if your buffer you choose for the first runs is suitable for the protein. And so, yeah, the use method. Sometimes you use too high a cross flow, a focus flow, for example, and can happen that it sticks on the membrane surface. That happens rarely, but it can happen. And yeah, then you need to screen different focus conditions, which can also cost you half a day. So it's very flexible. It can take 2 hours up to 2 weeks, let's say, in the most extreme case.
So the next question is a very practical one. I have a small hyperbranched polymer which measures Mn 3,400 gram per mole.
Yeah.
Molar weight is 10,000 and has a PD I of 2,5 by using SEC standard PS. Is it possible to measure this in FFF?
It's difficult, just because the cutoff of the membrane. You have to try that, because the PDI is quite, or the PD is very high with 2.5. So you can, I think that there's a lot of very small material, smaller than 2 kilodalton, and then I'm not sure if, then you have only one membrane you can choose, and then the sample has to work with this membrane. So that's something you definitely have to try. So I cannot say yes, it works, or it works not. So you definitely have to try that.
Okay, thank you. Next question is, how many different membranes are available now?
At the moment, we have the 10 kilodalton millipore membrane. That's a regenerated cellulose. We have a 30 kD regenerated cellulose and a 5 kD regenerated cellulose. Then we have PES membranes, also in 5, 10, and 30. And new in our portfolio is now the membrane from Sartorius. They have 2 kilodalton and 5 and 10. They have, for most of the samples, the same behavior than the standard regenerated cellulose from millipore, but for some difficult samples, they behave different. And also, it seems that they are better for organic FFF. And then we have some special membranes with the very low cutoff, but this has to be asked in our development department.
Yeah, since there are no further questions, apparently, we are at the end of our webinar. We will close the webinar with a short survey that will be shown in your browser, and it should give you the chance to hand out a short feedback to us. The next webinar will take part on October 25, and it will be about optimizing your method development for field flow fractionation with our Wired Scout software. Thank you, ladies and gentlemen, one more time for being our audience, and we hope to talk to you again in October. Goodbye.